in this video we will discuss about power of a lens and then combination of lenses. But before we go for this, let us discuss about sign convention. Generally, for this chapter we will use Cartesian sign convention. Another one is there, new Cartesian, but generally we will take Cartesian sign convention. Now, according to Cartesian sign convention, the thing is like this. Suppose this is positive x-axis, positive y-axis, negative y-axis, and negative x-axis. Now, if the lens, suppose if you keep the lens somewhere here, suppose it is a convex lens, like this. This is the optical center of the lens. Okay, object where do we keep? Here, like this. For convex lens, image is generally real image formed is generally real, so the real image is formed behind the lens, that means somewhere here. Okay, now in this case object is towards left, this is the object towards left, so that is why object distance will be taken as negative, because this is towards negative x-axis. Object distance we give it by u, so u will be minus in this case. The image is formed towards right means it is towards positive x-axis, so image distance generally we give it by v, so that image distance will be plus v. Okay, and remember that for focal length, the focal length of a convex lens is always positive, plus f. Alright, then again suppose we are keeping the lens here only, here, but this time for one case this convex lens also forms virtual image, right, when the object is placed in between the optical center and the focus. So suppose your object is somewhere here, image is formed somewhere here, which is the virtual image. So in this case object is also towards left, image is also towards left, so u will be what? Negative, v will also be negative, but focal length always positive for convex lens. Okay, so I hope it is clear. Now say the same sign convention we can use for concave lens also. In that case the thing will be like this, concave lens like this. Okay, then object we always place this side, so u will be minus, image will be formed same side, because concave lens always forms virtual image, diminished in size, so image is somewhere here, so in that case v will also be minus, because image is towards left. Okay, and remember that for concave lens focal length is always minus f, so this is the sign convention. Alright, now power of a lens. So generally power means it is the ability of a lens by which it can converge or diverge the light beams falling on it. We know that concave lens it diverges, convex lens converges. Means here I have given two examples. Suppose this is a convex lens, this is a convex lens, this is another convex lens. Now you can see in which of these two the converging power is larger. You can see that the light beams, these are coming and falling on the lens, and then immediately they are meeting at a certain point. The point is called focus. Here you see that the light ray is going like this, it is meeting at focus but after traveling a certain distance, right. Here it is meeting immediately, here it is taking some time. That means out of these two lenses, which one is having more power? This one is having more power, because it can converge the light rays immediately, but it can converge the light rays and it takes some time. So as a result power of this lens is more. Okay, in other word mathematically power is given by reciprocal of focal length. The SI unit of power is diopter, but SI unit will be diopter if the focal length is in meter. Remember that if the focal length is in centimeter, you have to convert it to meter to get the power in diopter. Alright, now another thing, Power is positive for convex lens because focal length is positive for convex lens, and negative for concave lens. So these are very important thing that you have to remember. Okay, another thing, here you see that out of these two lens, which one is having less focal length? This one, because focal length is the distance of the focus from the optical center. So here you can see this is the focus, this is the optical center, the distance between these two is this one, focal length. In this case the focal length is more, so power will be more in which case, because focal length and power, how they are related? Inversely. So power of this lens will be more, in that way also we can say. Okay, and power of this lens is less. Okay, from the mathematical formula we can say, or we can also say that since it is converging immediately, its power is more. Since it is taking some time to converge, its power is less. Then combination of lenses. So here you see, for combination of lenses we have considered two convex lenses L1 and L2. They are kept in contact in this way. This is the principal axis. Now when both the lenses are in combination, suppose their combined optical center is somewhere here, point C, combined optical center. Okay, but individual optical center also we have. For the first lens L1, this is the optical center. Second lens L2, this is the optical center. Okay, now this is the object. Light beam from the object is falling on the first lens. It is getting converged, and then suppose the second lens is absent. If the second lens is absent, then this light ray after converging, it is supposed to meet at which point? At point I1, and we are expecting the image will be formed at I1 when only lens L1 is present. But practically we have two lenses, so this light ray from lens L1, it will come and it will fall in lens L2, and lens L2 will converge it more. So as a result, finally image is formed at I. I think it is clear. So what is I1 then? I1 is the image position for lens L1. Only L1 is present, when only L1 is present. I is the image position, final image position when both the lenses are present. So we can think it in this way. In fact, in lens maker's formula also we took the situation in this way, that for first lens O is the object, I1 is the image for the first lens. For the second lens, I1 will behave like object, I will behave like image. That means the image formed by the first lens will behave like object for the second lens. I think it is clear. Image formed by the first lens is which one? I1. But as soon as L2 lens is placed, the image is getting shifted from I1 to I. That means this lens L2 is forming another image of I1 in place I. Okay, so I1 for lens L2 will be the object and I will be the image for lens L2. Okay, then let us see the distances. Object distance is U, which is generally measured from this point C, as we took point C as a combined optical center. V is the final image distance, that is distance of point I, and V1 is the distance of I1 from C. So for lens L1, if we apply lens formula, you remember the lens formula, I think, that is 1 by F is equal to, what was that? 1 by V minus 1 by U. Okay, for lens L1, if we write, in place of F I will write F1. In place of V means the image distance. For lens L1, which one is the image? I1. So what is the image distance? V1. So in place of V I will write V1. So that's what I have written here. Okay, 1 by F1 is equal to 1 by V1 minus 1 by U, given equation number 1. Then equation 1 we got. Next one is equation number 2 we will form, that is for lens L2. Okay, for lens L2 it will be 1 by F is equal to, same formula again we are using, 1 by V minus 1 by U. Okay, now you see here, okay, just a second, yeah, now you see here, for the second lens, where is the object? The object is I1. So what is the object distance? It should be V1, right? So in place of U, what shall we write? V1. And image distance, where is the image for the second lens? I. What is the distance of I? It is V. So finally the formula, and this F will be F2 this time. So the formula becomes like this: 1 by F2 is equal to 1 by V minus 1 by V1. Okay, this is given equation number 2. Then let us add this to equation 1 plus 2. So on adding, we are getting like this. This minus 1 by V1, and that side in equation 1 we have 1 by V1, so both will get cancelled, and we are getting this. Now see, 1 by V minus 1 by U, that is equal to what? 1 by F. And this F, this is the focal length of the combination of both the lenses, and individual focal lengths are f1 and f2. So I have written here f is the focal length of the combined. Okay, so if 1 by f is the if f is the combined focal length, then 1 by f will be the combined power, p, combined power. Okay, then 1 by f1 means p1, 1 by f2 means p2. So this is the equation, p equals to p1 plus p2. That means power of two lenses, we can just add them to get the combined power. Similarly, for 3 lenses there will be plus p3, 4 lenses there will be plus p4, like that it will go on. Now let us solve this sum. Okay, a converging lens means it is generally convex lens of focal length 20 centimeter and a diverging length of focal lens of focal length 50 centimeter are kept in contact. Find the power of the combination. So power of the combination means we are supposed to calculate P. So that means we have to find out P1 and P2 separately. So P1 means power of converging lens. Focal length of converging lens is given 20 centimeters. So power of the converging lens will be 1 by f1. But as I already told you that if the focal length is given in centimeter, to get the power in diopter, centimeter should be converted to meter. And how shall we do that? How will we do? We will do it like this: 20 divided by 100. It gives us the focal length in meter. So 100 will move up, and 100 by 20, it will be 5 diopter. So this is the power of lens 1. So that is why we have given here positive sign, because it is a converging lens. Next one, that is a diverging lens. The focal length is 50 centimeter. So that is why that will be minus 50. And as a result, the power P2 will also be minus. And since this 50 is also in centimeter, to convert it to meter, again we will divide it by 100. And finally we are getting minus 2 diopter. So first lens is having a power of 5 diopter. The second one is minus 2 diopter. When we add them, we are getting 3 diopter. Okay, so this 3 diopter is the power of the combination of the lenses.